Hi class, welcome to our online lectures. We'll see how this goes, and maybe it won't work out with my face down there, but we'll try it for a time or two and see how it goes. It feels a little bit more like being in a classroom. I kind of miss seeing you guys all out there, but we'll do the best we can under these circumstances. So today we're going to talk about the Milky Way galaxy, our own galaxy, and a bunch of the characteristics of it and things that we know about it. And get that to change pages. There we go. Okay, so our sun, as you can see in that picture there, is about halfway from the center to the outer edge, and it orbits in a slightly elliptical orbit at about 200 kilometers a second. So that's pretty fast, even though we don't feel it. It's kind of amazing. It takes about 250,000 years for it to orbit around the center of the galaxy just once. So it's a long way around. And since our sun is about 4.5 billion years old, it's orbited our galaxy about 18 times. So we talked about different types of star catalogs that have been done throughout history. Hipparchus did one way BC. Then we talked about Tycho Brahe and the man with the golden nose, how he did a star catalog. We've had spacecraft doing catalogs. The Hipparchus spacecraft did a bunch of measurements and mapped a bunch of stars. But our latest one is the European Space Agency's Gaia spacecraft. And it's been up since 2013, and it has been doing a lot of amazing things. So in the image to the right there, you can see how the Gaia spacecraft is orbiting the Earth, and it's looking at solar system objects, particularly a lot of asteroids. It's looking at the stars nearest the sun, stars that are way out in the disk and the bulge. It's looking at nearby galaxies and also in distant quasars, which we will be studying in another lesson or two. On the left side of the screen there, you can see what should look really familiar to you, an HR diagram. And the HR diagram here is amazing because they used over 4 million stars data. And their data is extremely accurate in distance and color. And they made this new HR diagram. So if you look at it, it's just a little different than what we're used to. The giant branch is kind of spread out all the way to the right and all the way almost to the left. The main sequence line isn't a skinny little line, it's kind of wide, showing that there's kind of a variety in stars as far as being on the main sequence. And then the white dwarfs, there's also a whole bunch of white dwarfs mapped on there that range from different sizes to different intensities and brightnesses and colors. So that is a really big advancement for us to see that accurate of information. Okay, so we just talked about how we can't really see our own Milky Way. We are stuck inside of it. So because we're looking out, we don't know exactly what it looks like, but we can measure it and plot it and estimate it. We can look at what's across the street and get an idea of what our house looks like. Let's look at ways we can map the Milky Way. So if we were stuck in our own house and we wanted to know what it looked like, we could measure the rooms, we could measure the hallways, we could plot and map and see how it looks and look at houses across the street and get those ideas. So that's kind of what we do. So some of the things we look at to map our own Milky Way is, first, we know that new stars are forming in the spiral arms where there's plenty of dust and gas. So if we look for those bright O and B stars, it's one way to find the arms. So the O and B stars are formed in those spiral arms, and they live most of their lives there because they're the big ones. They're the ones that die fastest. They might not even leave the spiral arm before they die. So if we start mapping where they are and we can see them because they're so bright, we know where those spiral arms are. We can also look for star clusters. Now we know all those big stars, and even the little ones, are all born in a group from a giant molecular cloud. And this happens to be a photograph of the double cluster. So there are two clusters in that image there. So star clusters would also be in spiral arms. So those are something else we could look for to map. The third way to map the spiral arms is to look for atomic hydrogen that's concentrated there. We call this H1. So atomic hydrogen on your periodic table would be the first item up there, and it has one proton and one electron. So how do we map that? When electron and proton are spinning in opposite directions, the atom's in a lower energy state than when they are spinning in the same direction. So you can see the pictures there, how they're spinning. On the upper picture, both at the same direction, and the lower picture in opposite directions. After about 10 to 11 million years, the electron may flip back to its lower energy state, emit a photon, and emit a photon in radio wavelength of 21 centimeters. From this, the distance can be estimated to give a type of a map. So mapping hydrogen. So this is kind of an odd picture, but this is kind of what they came up with when they started mapping the hydrogen. And it's not a very nice picture of our galaxy, but it shows that there are spiral arms, and in the image there's the sun at the top there, so you can tell that all the measurements have been done from that point of view. So that's why it's not quite a complete picture, because we can't see through the center of the galaxy to get the images of the opposite side. So this is what the artists come up with, and it's kind of pretty. We have our central bulge, which has a bar across it, and we have spiral arms that come off of it, which actually split after they come off a little bit, so it appears that we have a lot more of them than we actually do. And you can see where the sun is between those two spiral arms. Now we have learned that spirals, our spiral galaxies, most often have a bar in the middle. Not all of them, but some of them do. When universities try to figure out galaxies by putting data into a computer, having it run to create a galaxy, almost all the spiral galaxies will end up with a bar in the middle. So it seems to be just a natural phenomenon that those form. The brightest part of the galaxy consists of a thin, circular, rotating disk of stars distributed across a region about 100,000 light years in diameter and about 1,000 light years thick. So that would be edge on. And this again would be an artist's picture. Two spiral arms, Scutum, Centaurus, and Perseus, emerge from the ends of the bar and wrap around the bulge. The Sagittarius and outer arms have fewer stars than the other two arms. And there again you can see the sun's position there. And there is the Milky Way that we could see in a dark location. Only a few of you have ever said you have ever seen this before. If you go out of town in the dark, dark skies, when it's middle of the night, you'll be able to see a stripe across the sky, and that is looking into a spiral arm of our galaxy. So this is a picture. I'm going to show you a few images now of what the spiral arms have within them. So this is a star nursery. Right in the center there you can see really bright stars have given off enough radiation to blow away gas and dust. So they've kind of made a hole in the middle of this giant molecular cloud. But that is forming a star cluster. Now we have up in the sky, if you look early in the evening before it sets, the Orion Nebula is up. It's mostly You can mostly find it because there are 3 stars in a row that you can see across Orion's belt there. So across the belt are the 3 stars, and then hanging down from that is what looks like a little sword. And there are 3 objects there that look like stars, but the center object of the sword is actually a star-forming region that looks like this if you have a CCD camera. So that is a giant molecular cloud, and within it are many, many, many stars being formed. And we can see through that dust and gas with infrared cameras and see many stars forming in there, and a lot of them have planetary disks that are going to form planets around their stars. So these are a couple more star clusters, bottom right being Pleiades. You can see some of the gas that is around those stars. Within the spiral arms we also have planetary nebulas. If you remember, those are the dead, smaller stars that don't explode but gently die. And we have a lot of dead stars in our spiral arms as well. Here's another picture of a planetary nebula. This is a supernova remnant, so this was a large star that exploded. And this is another stellar nursery. You can tell that's in the spiral arms by how many stars there are. Just thousands of stars. So that's a giant molecular cloud that is also forming stars. And another planetary nebula. So there are 3 types of hydrogen that we find in our galaxy, and we designate them by H. So H1 is a single hydrogen atom, so it's 1 proton, 1 electron. We have H2 regions. This is a single hydrogen atom that's lost its electron, and these are in hot regions of space, and the proton is not able to hang on to its electron, so it blows off. So the H2 is exactly the H1 having lost an electron, so it's basically just a proton. The H2 at the bottom, we call the middle one H2, but the bottom one we call molecular hydrogen, even though there's a number 2 there. It has 2 hydrogen atoms that are bonded together. So that kind of hydrogen is what we generally find on Earth, because hydrogen likes to go around with its companion. It fills its shell by having 2 electrons merging together and holding that molecule together. So those are the 3 types that we find within our galaxy. So here you can see in the H1 region, the bubble on the upper right, that we have a nucleus of an atom with an electron orbiting it. In the H2 region, they have lost their electrons, and we're just seeing the nucleuses of those atoms. And this shows it as well. We have hydrogen on the left in its ground state. It gets excited by photon coming in, hitting it, and it was enough of an excitement that it actually knocks the electron right off of the hydrogen atom. So H2 regions look red. So these are the ones when the electron got knocked off, but the electron usually is attracted back to that atom because it's positively charged, the electron's negatively charged, so it's attracted back and it collects a new electron, and when it comes back and goes down to the lowest energy, it emits a photon, which is generally red. So when that happens in an H2 region, we get a red picture. So this is full of hydrogen that's hot. They've lost their electrons, and the electrons are returning and emitting the red photon. That is the Horsehead Nebula. All right, so these are called Bok globules. These are molecular clouds that have condensed and fragmented, and each one of those dark condensation blobs are forming stars within them. So they've mapped some of these H2 regions across the Milky Way, and it's hard to actually see them, so accompanying the hydrogen